Okay, picking up where we left off, we're going to start actually using Altium now. We're going to jump right into it. When we last left, we had set up we had installed Altium, we'd set up our license server. We're still connected to the license server here. Still connected to the VPN, still connected to the R drive. And what we're going to do is, we're going to start piecing together a schematic. So first of all, let's just look at the schematic. The schematic is shown here as a standard sort of schematic drawing. We have letters representing the vertical, numbers representing the horizontal. Usually in a schematic window, that's how you can reference something, right? You can say, look at the portion of the circuit in sector C2, right? And so then C2, right, it would be sort of around here, would be where you could expect to see that portion, right, if you were referencing it. And these don't have to get too crazy. The good thing about electronic design is we're not wasting paper by using multiple schematic sheets. So this project that we do for this class is all going to fit neatly on one, but if you have a bigger project, your senior design project, you have lots of components to it, you might want to use multiple sheets for clarity. So looking at the bottom right corner, you can see there is some logo stuff down here. I am going to zoom in. So one thing to note with Altium, the controls are a little bit strange. So right-clicking with your mouse, I'm right-clicking. Right-clicking sort of does the hand grab. Left-clicking is select. Middle, you can click the middle scroll wheel and it zooms in and out. You can use the scroll wheel to roll up and down. But control right-click. So now I'm holding down the control key. I'm right-clicking the mouse, going up and down. That zooms in and out. So zoom in and out, which you'll use a lot. Hold down control, right-click up and down. You get, after a while, you get just used to it. I have to think about what my hand is doing when I do that sort of stuff because I've been using Altium for a while. But again, right mouse click to pan, control right mouse click to zoom. So let's look at some of these things. So these are fairly standard. You'll see these in any schematic. You don't actually have to change these if you're just doing a design for yourself, but it's usually pretty nice. So you'll see these. It'd be really nice if we could click these, but we can't. It would be nice if we could click them and change them. We can't. What we can do is we can right-click somewhere on the schematic, and we can go. There's a couple of things. We can do preferences and project options. I'm actually not quite sure which one it's in. This is not going to be it. It's going to probably be in project options. So if we go to project options and we go to parameters, we're going to see parameters that correspond to all these things on the title here. So project title, and again, so let me just close this back up. I'm right-clicking. I'm going to project options, and then I go over to the parameters. So what about the project title? So that would be global title. You can pick a name for this. So I'll probably just call it EECE 320 PCB Airson. And you'll notice when I change that, it doesn't update it yet. It will. It'll update it soon. What's a revision number? So revision numbers are typically used, in any design process to show the iterations of the design, where lower ranking digits show more minor changes to the design, higher ranking digits show more major sort of, if you're making a large change to your design, you'd increment one of the earlier numbers. This doesn't really matter right now. I'm not even sure I'm ever going to change it, but for right now, I don't know, we'll just say 1.0.0. It should probably be 0.0.1. You know what? No. Let's make it... Oh, wait, what am I doing? I'm changing the wrong term here. So the value here, we'll make that... let's make it interesting. We've been working on this for a while. This is going to be version 6.5.13. That's how much we're working on this project. And global date, that can be... Sometimes that's set to be today's date. There is a way to have that be the day's date, but we'll just do 10/30/2020. So engineer and draftsman. This is an interesting thing, right? We have, what's the difference between engineer and a draftsman? Well, for this class, nothing. You are the engineer and the draftsman for this class. In the past, though, and in some companies still today, in larger companies, you'll typically see this. You have two distinct roles. The engineer sort of does the creative elements of the schematic design. The draftsman would likely be responsible for actually organizing a design done by the engineer. So the draftsman might actually sort of put these things together. This was more common back when these were done by hand. When they're done by hand, you could be a good engineer and be terrible at drawing things. Most engineers had fairly neat handwriting back then, not today. But you know, you could be a good engineer and not really good at drafting. And so a draftsman was typically a sometimes not really a professional. It was, you know, it was more like there was less creativity involved in it. It was sort of, you take a design, you put it in a nice, clean representation. And it can also mean, in the case of PCB design, it can mean doing the layout for the board, which sometimes, you know, again, in some companies, the layout is not so much a matter of engineering. In some cases it is. And so it's more blurred nowadays, but they still keep this traditional, who is the engineer who designed this, who is the draftsman. So that's going to be both. So we'll say this is... And then, yeah. Okay. So you'll see that changes it, but it didn't change this sheet title. It didn't change this sheet number. And so sometimes that, if you're on the sheet and it's active and you click properties, sometimes that's something you can see in the actual sheet properties. So yeah, like here, we should be able to see sheet title. So we'll just call this unified. You know, the whole design is on one sheet, so it doesn't so much matter. And sheet number, we can say this is 1. And that may not be true later on, right? If we end up having multiple schematic sheets, this is probably not going to be true. This nice little Western Washington logo, that's because when we started this up in the last video, when we created a new project, we created it using the WWU template. That WWU template was only available because we had the R drive mapped, and when we loaded Altium, it found that default directory, that R:/Altium/ whatever. If you're doing this, if you're working on this and you don't see that Western logo and your screen looks different than this screen, maybe go back and make sure that you have the R drive mapped. Make sure when you create a project, you create it from that template that comes off the R drive. So otherwise, I mean, it still might work otherwise, but other things, it's probably a good sign that other things are messed up if that's the case. Okay, so we've taken care of that. Again, I'm going to control, zoom, and right click and pan. So we have a lot of space to work with here. You generally want to try to keep your designs fairly tidy. So you want to keep them to the point where somebody can look at them and their eye is clearly saying, okay, I can see this section, this section, this section. You don't want to just throw a bunch of mess all over the, you know, anywhere there's a blank spot, you'll just stuff a different part of the circuit. You generally want there to be some flow, some left to right, top to bottom flow of a signal, for instance. You know, have it be neat and tidy. And one of the key things about being neat and tidy is you see down here in the screen this grid 10 mil here. That's referring to the grid snap. So it's basically saying our components are snapping to a grid. Right now the grid is set to 10 mil. I'm not quite sure what mil means in the context of a schematic sheet, but they use mil. They didn't used to. It's something they added, I think, around version 17 of Altium. But we can change that. We're going to basically want that to be as coarse as possible. So we're going to hit the G key. And you see hitting the G key, this thing goes from 10 to 50 to 100, 10 to 50 to 100. So hitting the G key and setting this to 100 is going to have our coarsest grid snap. It's going to snap. We're going to snap to these individual squares that are shown here on the grid if we're set to 100 mil. And I think that's just kind of assuming we have 1 inch. Each one of these squares is 1 inch by 1 inch, so 1 mil or snapping to the square. So this is not just a matter of being neat and tidy. This is also one of the biggest mistakes students make when they're doing a PCB design is they'll have a wire that they think is connected to a pin that's not. So sometimes it can be very hard. If you have a pin that's off of a wire just by a little bit, if you didn't see it didn't connect when you did the connection, it can look connected but not actually be connected. And it can be very difficult to see that error later on in your design. You can miss it. It's easy to miss. So for now, We're going to set the grid as coarse as possible. It's going to help us not only keep things tidy, it's going to reduce errors, and we're going to get started. So a couple things to note when you're looking at this, you know, you have some standard. We're not going to talk about everything that's here. There's, like with any piece of software like this is an enterprise software. There's a lot of functionality. This is software that's used by the biggest companies on earth and small companies. And you know, small companies and us, we might only use 10% of the functionality of this software. Big companies might use a lot more. So there's a lot here. A lot of it you can ignore. A lot of it my eye just kind of naturally ignores. I don't usually use most of this stuff, for instance, on the screen. Okay, but a couple of things to note. We have here, over on the right side, the Explorer. It looks like we're not connected here. Could be a problem later on. It's a little different. This version is a little bit different. So let me see if it looks like I've got what I'm going to need. Shoot. Okay. Wow. Sometimes we rely on that Explorer. We don't have to. We have libraries set up, but so looking at this right here, one of the biggest things is, let's say you have like components and you were looking at components here and you were relying on it, and then you accidentally like popped the components out and you're like, oh, okay, we're popping them, all right, it popped out, and then you go, I don't need that anymore, get rid of it, and now components are gone. So if things go away, you can almost always find it. If things go away on this side, you can almost always find it down here in this panels button. So you can go to panels and we can put the components back. Back where it needs to go. So there's some useful tabs here. A storage manager, I'm not sure is that useful. I'm not sure I've ever used it. The Explorer normally, you know, let's just have Altium 365. I guess the manufacturer. Okay. All right. I think everything will be here. I'm sorry for the delay. I'm learning along the way. Also, keep in mind about this video series, I'm doing everything start to finish. I hated when I was in school and I would have an assignment or a project and I'd be given instructions on how to do it. And it would say, oh, just do this. And then it's when you try to do it, it's not really clear how you do it. I hated that. I hated it. And so I'm going to try to make sure that doesn't happen. So we're basically going to go through this start to finish. And everything, you're going to see it live with me. But like when I do stuff like this where I'm like fumbling around, remember you have the speed up key, you have the zoom key. I'm not going to skip this stuff, but you have the power to. So if you feel good about this part and you don't want to watch it, skip past me. If I'm going too slow for you, because I'm just a slow person, I'm slow but not methodical. It's weird. Some people say, oh, people who go slow, they're careful and methodical and neat. I'm neither of those things. I'm not any of those. So I'm just, I don't know. But you use the power of this being loaded on YouTube to skip past the stuff you don't want to see. Okay. So we're just gonna start learning by example. I'm just gonna start piecing things together. The first thing is the components that we need to use for Altium. So there's a lot of sources for components. So if you go to components here, you can look down. There's a couple of default libraries. So this PCB and schematic library, this was built into the preferences. This isn't through the R drive. These are not really what we're going to be using for this class. We have a special parts library that we'll use, and I'll show you how to get it. But there are miscellaneous devices and miscellaneous connectors. So these come with Altium. These are just library parts that come with Altium, and these can be really handy. So some of these can be are just really useful. Like if I want a 2-pin header. If I want a 2-pin header, I can just, it's just a standard 0.1 inch space dip header. I can just find header 2 in the standard connectors, right click it and go place header 2. And actually this is a good demonstration of the grid, right? So you can see that grid, we're snapping to those grid lines. And whereas if we were at 10 mil resolution, look at that, right? It's very easy, right? If we were 10 mil resolution, we drop our header. I hit escape, by the way. I hit escape to cancel that. And then we draw a wire. It's possible look, so we just drew a wire, and when we're zoomed out, oh, it kind of looks like that wire is connected, but it's not. So that's one of the downsides, you know, one of the benefits of using this coarse grid is this doesn't happen. So I'm going to go back, I'm going to set my grid to 100, pop this on a grid, and then, well, actually, we're going to need to use a header, so I'll leave that on there later on. Well, notice when I placed this header, it says P, which is the label for port. That's the standard IEEE format prefix for a header, or for a port, for an off-board port, is P, and there's a question mark here. The question mark is because this doesn't have a number yet. So whenever we have components, if I put down 10 of these would all be called P question mark. But eventually we have to give these a number, right? P1, P2, P3, P4. Resistors should be R1, R2, R3, R4. Everything has to have a unique name in order to identify it. And what this is saying is just saying you haven't given it a name yet. And I'll show you, normally we don't add the names manually. There's an automated way to give these things numbers that correspond to their prefix, to their character prefix. And I'll show you how to do that later on. But for now, just note that this will eventually be a number, but right now it's a question mark saying, oh, I don't know what number it is. Okay, let's load the libraries we need. So if we go to, if we go back to our, okay, so if we go back to our R drive, so we go to this PC, we go to the R drive here. If we go in the Altium folder, you'll see this folder called Libraries. Now this has WWEE library. That was what was loaded up here. But there's also a folder here called 320. And this 320 folder has the parts that we're going to use for this class project. There's a couple of extra stuff in there from old class projects, but these are the ones we're going to use. And I highly recommend, because so Altium, the speed of using Altium is heavily dependent on its connection to these things. So I like to make a local copy of these. If you don't have a really fast connection to the university, make a local copy. So just take these two things, just Control C, and then, you know, go back to, like, I don't know, Documents, new folder. Let's just make a folder called Altium. Whatever. So I'm just going to put these libraries in here. I'm just going to make a local copy. And the benefit is, if my internet connection to the university is slow, it's going to be much faster. It's going to be a lot easier to use Altium if we have a nice fast connection to these parts. So now that they're in that library, or now that they're stored locally on my computer, I can go back to the components, and I can go up here and I can do File-based libraries preferences. And this shows any libraries associated with the project. You can have libraries associated with just the project, and installed libraries. So what I'm going to do is I'm going to install a new set of those libraries that I just copied over to my computer. I'm going to install those. So I'm going to go to Documents, Altium, and I need to change it to, I'm just going to change it to all files, and I'm going to select both of these, and I'm going to open. And now these 320 parts are installed. So now what we can do is, if we go to 320, and we're going to want to go to the schematic and we're going to want to go to the schematic library. So I mentioned in the previous video, every component has a schematic representation, and it also has a physical board representation. So that's the schematic and PCB library are sort of the two sides of that same coin. We load them both so that the schematic file has in it a reference that says, here's where the footprint is for this particular part. Here's where the footprint that says, you know, how it's physically designed is. And also it says, here's which logical pin connects to which physical pin. So that's kind of an important thing. So now that when I go to this library, when I go to this 320 parts.schematic library, I see all of these components. And you can scroll through here and take a peek. I sort of went through and added components that I thought we need for this project. But let's start at the input of this. So the way this project works is we're going to have the entire board is going to be powered or charged through a USB-C connector. USB-C connectors are a really nice connector because they're reversible. So you don't get that typical USB issue where you put it one way and then put it the other way. And it's also a really robust connector. It's got a steel shroud all the way around. So it's got a steel plug, a steel shroud, So you can really kind of yank on it and it doesn't do a whole lot of damage. Well, you don't want to, but I mean, it's much more resilient to damage than some of the older ones, especially USB micros, which had an issue. USB micros, USB minis, both of those had issues. USB-A, I don't think ever. USB-A and B are much better, but USB-C is just a good connector. And so we're going to use it in this class, but we're only going to use it for power. We're only going to, this is just going to be, you plug in a USB-C, it provides power to the board. Looking forward, what's going to happen is USB-C is going to provide power. That power is going to be used to charge a battery. That battery is then, the battery is going to be a lithium-ion battery. It's 3.7 volts. That 3.7 volts is then going to be boosted up to 5 volts. And that 5 volts is going to drive our circuit. So we could just take the USB-C connector, which is a nice clean 5 volts coming off USB-C, and we could just power our circuit directly. But to add extra functionality for this project, I wanted to have that battery component. It hits more of the outcomes for this class. You learn about how to use battery chargers and boost converters. So for the way we use it, we are going to have that USB-C connector as something to power the battery charger portion of our circuit and really nothing else. So let's add a USB-C connector. So again, schematic library parts, not USB micro, we're going to go to USB-C. USB-C. We can click it and drag it. Sometimes I like to right click and go place, but I just clicked and dragged that time. So I'm a little zoomed in. This is a little tough right now. Okay, now a warning. This was a part that I made. So I designed this part. It looks a little cheesy, a little USB circle. A couple of things to note. So it's got it's a port, it's a connector, it's an off-board connector, which is labeled with a P question mark again. So now we have 2 P question marks here. It's got this pin is numbered 7 that's shown connected to this outside. That's the guard pin. It's sort of the ground, the shield pin. So this is a pin that's not an actual logical pin. It's not a pin that sends signal. It's a pin that just touches the shield of the USB connector. Normally you want this, usually you want this to be kind of static protected. What we're going to do is we're just going to connect it to ground. So we're not going to worry too much. We're just going to connect the shield to ground, which is a fairly common practice. You might not. You might, if you were doing a different design that really had to be protected against potentially high current, high current static discharge events, you might have it connected through like some sort of shock suppressor, through some sort of like electrostatic discharge suppressor circuit. We're not getting that fancy though. We're going to keep it simple, so we're not going to do that. So, but this is 7. This is pin 7. You see this pin, we have VBus, ground, CC1, CC2. There's 2 numbers on this VBus. So what this means is that this logical VBus, so we have the pin that represents the bus voltage, which should be 5 volts for USB. We have the pin that represents the ground, which is the ground for the USB. CC1 and CC2, we'll talk about those a little bit later. But when there's 2 numbers, it's saying that this logical pin corresponds to 2 physical pins. So there's 2 physical pins on the connector that's VBus, and there's 2 physical pins that are ground. Why might there be 2? Well, remember, this is a reversible connector. So if you want to have a reversible connector, you always have to have, like, anything you want to have stay the same. Even if you flip the cable, you got to have at least 2 of them. So that's what's going on here. Is there's 2 pins corresponding to the top and the bottom VBus and ground connections, which are kind of on opposite sides. So if you flip it, it all stays the same. So 2 physical pins, 1 symbolic connection. Okay, so CC1 and CC2. The USB-C standard, being a reversible standard, has an extra little feature, which is this CC1, CC2 connection, which does 2 things. 1, it helps the system determine the orientation of the cable. So even though you're allowed to flip it either way, the system knows which way you had it flipped. And the way USB-C cables work is they basically carry multiple USB connections. It's basically like if you took a USB cable and another one that was facing the opposite way and you just plugged them in twice, right? It doesn't matter which way you flipped it. One would be on top, one would be on the bottom. The only difference would be your device would be plugged into a different physical USB connector depending on which way it flipped. Well, that's the same thing with USB-C. It's multiple USB connections. If it's flipped, it's just a different connector on your computer connects to a different USB connection on your computer connects to a different physical device that's connected to that USB connection at the other end of the cable. Well, the CC1 and CC2 pins also allow you to specify how much power the device is able to draw. So by default USB devices draw 100 milliamps. If they're registered, if they identify themselves, they can draw 500 milliamps. USB-C allows them to draw up to 3 amps. And actually, USB-C, there's extra features you can use to actually allow really fancy power connections. So there's ways for a device to communicate with a host to say, you can give me 15 volts, and I can take 15 volts. I don't know what the highest is, maybe 24 volts, 4 amps. I don't know. I can't remember the exact thing, but basically it's possible to send higher voltages over the USB bus. That's something you really got to be careful with. So there's definitely a careful handshaking before that happens. But right now we can basically tell, by setting a certain resistance value to these CC1 and CC2 pins, we can build a device which, when we connect it to a host over this USB-C connection, the host is aware, okay, this thing is capable of receiving this much current, so we'll provide it this much current. And if it tries to draw more current than that, we're going to cut it off. So how do we specify that? Well, for our purposes, we want to tie CC1 and CC2 to ground with a 5.1K resistor. Now, on the other side of it, on the host side, CC1 and CC2 are connected to power, to the bus power, by a different value resistor. So basically, CC1 and CC2 are tied to different value resistors at the host and the client connection. And the voltage that's produced by that divider between those lets the host know, and the client, I suppose, know how much power the host and the client can give and receive. And so it's kind of a simplistic way of doing that sort of signaling, but it works. So for right now, all we have to do is we have to connect a 5.1K resistor from CC1 to ground and CC2 to ground. So how are we going to do that? Well, let's get some resistors right now. So let's go to our components. Let's go to the miscellaneous devices library. Scroll down to resistor, and the resistor we want to use is Res3. And, oh, what did I do? Maybe it's not. Maybe it was Res. What am I doing? Okay. Yeah. So here's what's going on. So I clicked Res3, and this is a Altium provided part. And then I want to go down in this sort of details, and I want to go to models, and I want to choose this one. I want to choose the 0603 version. 0603 is a way of saying this resistor is going to be 6/100ths of an inch by 3/100ths of an inch. So this is a surface mount resistor, so they're fairly small, but 0603, 6/100ths by 3/100ths. This is the size resistor we have in the parts cabinet. 0603s are small enough to make a reasonable circuit, but they're big enough to use by hand. They're big enough to move around with tweezers by hand. The 0402 is kind of the limit for doing with tweezers by hand. We do 0603 just to be a little more comfortable, just so you can be a little more jittery while you're working with this. So we're going to make sure we have 0603 selected. Res3, and then I just like to right click and go place Res3. So I'm going to hit the space bar to rotate this. So hitting the space bar rotates. I'm going to place one here-ish and place one here-ish. And then I'm going to hit escape to cancel placing these. Now, what I'm going to do is I'm going to double click this 1K, and I'm going to change it. These are 5.1K, so I'm going to 5.1K. 5.1K. Okay, what have I done by changing that? I changed it from 1K to 5.1K. Did that do anything? All that did was change the label. The thing is, with these components, physically they're the same thing. As far as design goes, they're the same thing. If it's a 0603 1K or an 060K 5.1K, it's the same as far as the software is concerned. It's the same footprint, the same connections, same everything. What we're doing, though, is we're changing the label so that we know, so that when I assemble this circuit, I know, okay, this resistor needs to be an 0603 and it needs to have a value of 5.1K. And that's on me. That means I have to go to the parts cabinet and I have to choose the 5.1K resistors. I have to you know, keep it separated, make sure it's the right one, put it in its right spot on the board. But changing this label didn't do anything physically to the design. All it did was change the information provided to me when I'm doing the assembly. Okay, so now I need to wire these terminals to here. This is the wire button. So place wire is this little wavy thing here. I'm gonna click that, and now you see the little, it's easy when we snap, right? It's easy when we have grid snap set to 0.1. It's a lot tougher if you don't have the grid snap set to 100 mil. So the grid snap set to 100 mil, this thing pretty much pops in here. So we're gonna click one side to CC2, and then click the other side here. And then one side to CC1, and the other side. And see how it turns like big and blue when it's actually touching the pin? That's important to check for, to see that. Other side to CC1, okay. And then we're gonna hit escape to cancel wire selection. Now we've successfully wired our USB CC1 and CC2 to these pins. The other side of these pins needs to be connected to ground. Well, ground is over here. So one thing we could do is we could run these wires over here, run another wire, and then we could drag this ground everywhere. But it's easier just to label the ground and say, this ground is a signal called ground. Anywhere we place that signal is gonna be our ground. So what I'm gonna do is I'm gonna click this ground power port here, click it, and then I'm gonna place it here, place it here, place it here, hit escape to cancel. Okay. Now, first of all, why did this just put a blue dot here? It didn't put a blue dot here or here, it put one here. Well, this little 1 in 6 that you see here is a trick that we did in Altium. So this 1 in 6, this is actually 2 pins that are on top of each other. And you can't see it. It looks like 1 pin to you. It's 2 pins stacked, pin 1 and pin 6. So when I put this ground here, it physically connected that ground to 2 pins simultaneously. And so it gives us a big blue dot to tell us, hey, you're connected to more than one thing here. So it's good for your eye to know that. The reason that's a little weird right now is because you don't see that it's 2 pins, but that's how we got the 2 pin labels here. It's kind of a downside of Altium. Most of these EDA softwares allow you to take a pin and specify that this pin maps to 2 physical pins. In Altium, you kind of just have to do 2 overlaying pins. You have to do this sort of a trick. Now these ground labels mean, you know, it looks like they're not connected, but they are. This ground is just a fancy label. So we could have labeled this Fred, and if we labeled all 3 of these Fred, the software would have known that these are all actually connected together. We're just making it a little more clear by calling it ground, so there's not so much ambiguity. So this is ground. We also wanted to ground the connector, so let's ground the connector here too. Okay, what about the VBus here? Well, the VBus here, we can, if we want to, label this. Yeah, let's go ahead and label this. What I'm going to do is I clicked this power port here, and I'm going to put it here. And then I'm going to hit escape. I don't want to call this VCC though. VCC is kind of a generic term for the power supply for our system, but this is just the power from the USB bus, which is just going to charge the battery. And then we're not going to use it other than that. So I don't confuse myself. I'm going to call this, yeah, maybe just VBus. Maybe VUSB. How about that? Okay. So now anywhere where I take one of these power ports and name it VUSB, the software knows these things are physically connected. Okay. Before we get too far, let's see what this looks like as far as the physical board is concerned. So before we get too crazy here, and this is the way I generally do designs. I do a little bit in the schematic, and then I do a little bit in the board and make sure everything is nice and what I want, and then I go back and do a little in the schematic, and then I do a little bit in the board. We always, with Altium, they want to save often. So the biggest mistake students make with Altium is they don't save and it crashes, and then they lose a bunch of work. So we've done a good 15 minutes of work if I hadn't been blabbing here, or we've done about 3 minutes of work if I hadn't been blabbing. It turns in 15 minutes. I'm going to look at this project here. I'm going to right-click it, and I'm going to go save. So save the project. But now I just saved the project. I didn't actually save all the files. So what I can also do is I can click here, and I can go, oops, file, save. Alternatively, I could have gone up here and I could have gone save all. So I could have just saved the project and all the documents all at once. But I just wanted to note that just because you save the project file doesn't mean you're saving all of the files that are a part of the project. So you got to be really careful. Look for that little red document to show that the project has been changed. So there's a couple things we need to do. We've placed some components right now. I'm going to zoom out. It's in a pretty good spot. It's in a pretty good spot. And we have this little header down here, which I'm just going to ignore for now. But now, again, we still have P question mark, P question mark. So we need to give these actual numbers. We could manually do this. We could go in and give these numbers. We could give these R1, R2, P1, P2. But there is a tool you can use. So you can go Tools, and it's called Annotation. Annotation is this process of giving each component a number that corresponds to, its order in the circuit. Usually it corresponds to its order in the circuit physically on the schematic, but it ends up kind of referring to its order in the order that you created it if you're not sort of careful. So we can do this Annotate Schematic. If we do Annotate Schematic, it's going to take us to this menu that tells us all the things that need to be annotated, and it tells us, well, you know what, let's just do it. Let's do it. So we'll go Annotate Schematic. Couple things, how it annotates. You can do the order for annotation. So what it's going to do is it's going to go from the top left corner of the page. It's going to look for any part that's missing an annotation, and it's going to give it a number. So top left would be 1. Further right would be 2. Down and to the left would be 3. Then to the right would be 4. And continues. Kind of goes in the order that you read a page. That's fairly standard. So this is telling us all the things that need to be changed. So it's basically saying we have 2 resistors and 2 ports that need numbers. So we're going to give them numbers. And so if you want to go through this page, there's a lot of detail here that you don't really care about. All you do is click Update Changes List. And now it says, oh, I'm going to call this one P1, I'm going to call this one P2, this one R1, this one R2. So after you've updated the changes list, you have to do accept changes, create ECO. What's this ECO? It's an engineering change order. So this seems really big, right? All we're doing is numbering these parts, and it created this change order, right? This is because this software is meant to be used in enterprise companies, right? This software is meant to be, the people who are building an iPhone circuit might be using this software. And so for them, changing a resistor value from R1 to R17 is kind of a big deal. It's not so much a big deal for you, but it's a big deal for them, because you could have a team of 100 people working on this. And if somebody's going around changing the numbers, it's gonna cause an issue. So the software is designed to accommodate that sort of stuff. It's designed to accommodate these companies where even small changes to a circuit can be a big deal. So it goes through a process of change orders that sometimes needs to be approved. So I could set this up so that you couldn't make this change until I approved it. So then you would create a change order, you would execute the changes, validate, execute, and then get it approved, and it would be a long process. For us, we can just do it ourselves, right? We can just execute changes, close. So if we close this out, now R1, now why is this R1, right? It's to the right. Well, this resistor was a little bit further up than this one. This one was a little bit higher than this one. So because we were doing top to bottom, left to right, the first thing it did is it did the top row, and because this resistor was a little bit higher than this one got the R1 label, this one got R2. Does it matter? No. It might be better because R1 is connected to CC1. It really doesn't matter though for this. So everything is labeled now. So and now you see the file changes. So now we'll just do a save all, clean them all up. All right, so now what we need to do is we've specified in the schematic, I have these components. These components are connected in these different ways. And each one of these components has associated with it a physical footprint. So if you click on the USB connector, for instance, click on the USB, click on the USB connector and then go to Properties, which you can also do that if you click on anything and hit Tab, I believe. No. Is it? I forget what it was. I thought it was. I forget. Is backspace? Anyway, whatever. I'll double click. You can also click on you can right click on a part and go Properties. You can click on the part, get properties over here. You can double click it. The thing about Altium is there's a lot of ways to get to the same information. So don't let it overwhelm you that there's lots of information and lots of ways to get to it. It's just, you just kind of get used to it after a while. But one thing you'll notice when you click this part and you go to footprints, there's a footprint here. So there's this, look at that, right? There's this footprint which is associated with this part. So, and you'll also notice there is I don't see the pin mapping, but yeah. But anyway, we have that linked footprint. And so when we modify the board, this schematic just detailed the physical part, the physical connections between those parts, so all of that information can get reflected on the board side of things. If we go to the board right now, though, if we click on the board, it's empty. It's just this big empty blank space. But if we want to move these changes that we made in the schematic over the board, what we do is we do Design, Update PCB Document. So now we're going to update the PCB document, and it's going to pop, once again, it's going to pop up this change order that says, okay, here's all the things you're about to change, which could be a big deal at some companies. For us, we don't really care too much. So it's basically saying we're adding these components. You're adding this P1, P2, R1, R2. You're adding these signals, these nets, ground, VUSB, and then what's this net P13, net P14? Those are names that it gave. We didn't name these nets here. So these are names that it just assigned to the nets that we left unlabeled, which is fine. We don't have to label them. We know it's CC2 is connected to R2. I didn't need to give this a name. We don't need to get too formal about this. And then I'm just going to go to Execute Changes and close. And now look at what it did. Now it automatically popped us over to the board view, and it threw our 4 components on the board. So it actually threw them off the board. This dark black area is the board space. The components are right here. What I'm going to do right now is I'm just going to just drag a select, left click, drag a select over them, left click again, move them onto the board. I'm going to move them up to the top corner of the board. I don't know. Bottom corner. Maybe I'll move to the bottom corner. So what do we have here? I'm going to zoom in. So holding Control, scroll wheel, now right click to pan. We have this one that I don't care too much about. So this is our USBC connector. It doesn't look like a USBC connector necessarily, but you'll notice it has these associated pads with it. It's got these pads that are that make surface mount connection to this actual part. It also has through holes here. The through holes are for the pins, for the physical. The thing with USB is about an electrical connection. It's also about a physical connection. So the through-hole connection for USB gives a nice, rigid, physical connection of the connector to the board that we don't rip it off. And a lot of you probably have in the past, you've broken electronics by ripping the USB connectors off. For a while, there was a lot of USB micros that had surface mount only connectors, and those don't tend to last too long. So they found with the USB, it's good to have through-hole connections. It's good to have a nice, solid solder connection of the actual connector to the board, and that's what's going on here. So, but we can... this is now a part that's on the board view that we can move around. And you'll see these little lines here. What are these little lines here? These lines are called air wires, and they show the connection between components. So basically, because if we go back to the schematic, we had specified with a wire that this CC1 pin 3 is connected to R1. So what we see is, if we zoom in, CC1 pin 3 is connected to R1 here. And now I'm hitting the space bar while I move it around, I'm hitting the space bar to rotate it. One neat thing about air wires, if you can see that, or maybe it helps if I zoom out, if you can see that air wire, it can show when they're twisted. So right now, this pad wants to connect to this pad and connect to ground, and this pad wants to connect to this pin. So right now, these are kind of twisted across from each other. It's not fully true because we also have a ground signal up here. An air wire always connects the closest pin that it needs to be connected to is what it shows the air wire to. So if I move this part a little bit further down, the air wire is going to jump to here. It's going to jump to this pin. If I move it a little further up, oh, now it's going to jump to this pin. The air wire is just showing the connection to the closest thing that has that same signal. So let's just move these. I'm going to move R1 here-ish. Another thing I noticed, as I move it, I'm kind of getting smooth movement. I don't necessarily like that. So I like grids. I like snap grids. So I'm going to hit the G key again. And hitting the G key pops up this snap grid menu. So I'm going to snap to... for now, let's snap to 0.25 millimeter. It's a little coarse. No, it's not. Let's snap to 0.5 millimeter. There we go. It's a little coarse, But that's okay. It helps us keep things neat and tidy. It helps us keep things aligned. If your grid is too fine, it might look like two things are aligned, but they're not really. So let's move this USB connector kind of near the edge of the board. We can even have it sticking off the edge of the board. That's okay. We can even move the board later on. We'll talk about that. And now let's move these resistors. So this one looks like it wants to connect to that pin. This one wants to connect to this pin. So moving the resistor, hitting the space bar. Looks pretty good. Moving this one, hitting the space bar. Looks pretty good. Yeah, we can move these a little closer. You don't need to get things too compact. If you get things too compact, it can be hard to assemble these things. Especially this USB connector is very likely a lot higher than these little resistors. So if you get a little thing too close to something that's really tall, it can be hard to get a soldering iron in there. So we're going to move these like this, and we're not going to worry too much about this port right now. And I want to show you one more thing. So I want to show you one more thing, and that is I want to show you the 3D view. So all of these parts, we have a representation right now in 2D, which is showing the signals. This red is showing copper that's on the top of the board. So it's this top layer copper. Blue would show copper on the bottom layer of the board. So the boards that we use are going to be 2-layer boards. If you go fancier, you can have 4-layer boards, 6-layer boards, 10-layer boards. iPhones, I think, now are 12-layer boards. If you're working in military applications, sometimes you'll have 20-layer boards. You know, they get crazy. But it's a different color. So right now we're seeing red representing top copper, blue representing bottom copper. These gray pins are representing copper on both the top and the bottom. So these are like this is like a ring on a hole in the board. But we can also view these in 3D. So if we want to view these in 3D, we can hit the 3 button. So I'm going to hit the 3 button on the keyboard, and that takes me to the 3D view. So to zoom out, I'm going to hit Control, hold Control, do scroll wheel. To rotate, I'm going to hit Control right. Sorry, zoom is Control right click. What am I doing? Okay. Sorry, to rotate, I'm going to hold Shift. If I hold Shift, it pops open this little sphere that I can turn. Shift, and then I'm going to right click, and it lets me kind of grab this little ball. So if I hold down Shift, it creates the little ball. If I right click, I sort of am rolling the ball back and forth. So this is now I told you I made this USBC connector, so I went a little cheap. It's just a little box, a little rectangle. It's a abstract representation of the actual thing. And then my resistor to these little things. So you can kind of see, right? If this thing had been really close, if this had been really close, we might not have been able to easily get to those resistors, and we might not have been able to easily get to these pins either to do this soldering. So it's something to keep in mind. Let's go back. Let's hit the 2 key. If we hit the 2 key, we're going to go back to our board view. Hold down Control, scroll wheel to zoom out. Hold down Control, right click. Right click to pan. We have these labels, these annotations. These are silk screen. So in addition to copper, there's also solder mask and silk screen on a PCB board. These are things that are going to show up as white ink on your PCB, on your final board. So it's good to put indicators that tell you what things are. We want to know that this is R2 and this is R1 because we have to go back and see what value resistors these have to be. But right now, they're looking a little big, these little labels here. So if we hit 3 and go back to 3D view, yeah, they're a little big. The label's bigger than the component. What we can do is we can click on this, we can double click this, and it gives us this information about this. It gives us the text height, so 60 mil. We don't have to be quite that big. So we could be probably 30 mil. And a mil is 1,000th of an inch. So 30 mil would be 30 thousandths of an inch. So 300ths of an inch would be the height. If we do, it's going to be kind of fat if it's 30 mil and 10 mil. You can take a look at it. If it's 30 mil and 10 mil, you got kind of these chubby little letters here. So let's switch it to 6 mil as our stroke width. And that looks pretty good. So that's a little bit better. We can kind of align this to the top. Looking great. Now we can do that for all of these, or another thing we can do is if we just select all of these components, we can go properties, we can go to height. So it did a star because I had already changed one, so they had different values. So we can change the height to 30 mil, and we can change the oh no, that's not what I want to change. Whoa, sorry. All right, let me go a different way. I'm going to click one of them, and I'm going to right-click it, and I'm going to go Find Similar Objects. Ah, okay. Now string type designator. Okay, text designator, same, and I click Apply. So now it's selected all the designators. So now if I go to the properties, now I can change the text height to be 60 or to be 30 mil, and the stroke width to be 6 mil. Okay. So I'm able to change a lot of them at once. So I can put this P1 down here so I can see it. R2, R1, P2, I'm not, again, I'll get to that later. And then now if we look at the 3D view, much better, right? Looks a lot better here, a lot cleaner. And we don't have to do this right now, right? We could do this later. I'm just kind of trying to step you through this interface and the interaction and what these different things mean. And again, always save, right? So file, save all. Okay. I think that's just about good enough for this video. When we come back, we're going to add more components. When we come back, we're going to add more components and we're going to start doing wiring. So we're going to get into, we're going to add more components. We might add the battery charger. We're going to do some wiring, and that'll be step 2. So thank you for watching.